The moment I put it this way, most of you started, in fact, notice the capacitor stage. You thought it's like so many things, right? But by the time we came to the inductor stage, we almost you started feeling things easy, right? And like I know this kind of feeling. That is good. And although it is kind of organized, you were feeling one side of it yesterday. It looks cluttered right now. There is two important formula here. Z is 1 by j omega c for a capacitor. Impedance. This is essentially the resistance is no more independent of frequency. Resistance is dependent on frequency. Resistance is essentially voltage by current. Here, impedance is essentially voltage by current. Impedance essentially is resistance. Difference being, here for a resistor, it acts instantaneously. There is no time dependence. There is no frequency dependence. For a capacitor and an inductor, that is not the case. So for a capacitor, this impedance, the resistance like thing depends on frequency in a complex way. Complex as in there is also this complex number square root of -1. At the end of the day, it's just V by I, right? So in fact, based on this, we solve this capacitor question. We got to a stage where we can comfortably solve purely resistor-based circuits, resistive circuits. They realized this, they give a RC circuit like this. Many of the questions essentially boils down to a purely resistive circuit. Given circuit as a capacitor, but under steady state condition, initially this, that, and all that, typically it becomes a simple resistor circuit. When the capacitor opens, when the inductor closes, and all that. So we have discussed that. So that is where we stand. And we also know that they could actually ask here, there is a steady state here. Before the switch was closed, there is a steady state here. They could ask things here and there just be, 0 minus and 0 plus. And they asked it after a long time steady state, t tending to infinity. They could technically ask anywhere in between. They can ask you for voltages. They can ask you for energies, right? Any particular time. And once again, tau is RC. RC circuit, tau is RC, right? Once you know that, you can get voltage as a function of time. And once you have that, you can also have energy as a function of time. They can ask any point in this graph. It boils down to. Here in this question, they asked you this point, the green point. They give an inductor. They give a L over R circuit. Okay. This is referred to as an RC circuit. They give a circuit with an inductor and a resistor. I call this L over R because that happens to be the time constant of this circuit. Again, the text typically suggests they are referring to steady state or initial condition. They are referring to a purely resistive circuit. And then in this case, so is there a switch? Yeah, there is a SVDT switch. So there is an initial steady state current in this inductor. We can easily find it because an inductor shorts. There is this current. So we know the initial energy stored in the inductor. Once you turn that switch, what drives current in the circuit is this initial energy in this inductor that eventually gets dissipated through the resistors. So the energy dissipated in the resistors is essentially the initial energy stored, okay, that you could easily find. The initial current in the inductor, you could find this, right? So this is where we left, and let's continue with this discussion here. At this stage, one thing I want to notice is, so I will solve this problem again. Perhaps I kind of did it too fast. The main reason being, like, I spent a lot of time with the capacitive circuit. There isn't like a big difference. Once you could understand the resistor capacitive circuit, this last column is fairly easy to fill up, right? I'll do that anyways once again, but the same discussion holds here. They can ask you energy or voltage at any time or current at any time. Even notice. So I mentioned all these things, right? So given voltage, you can find energy, right? Half CV squared is a function of time. You could also do one more thing. You can also find current. How do you find current given voltage? A voltage is this exponential saturating function. And as you know, voltage is a function of time. It's exponentially saturating curve. How do you find current as a function of time? Hello. Voltage is a function of time. Is there, how is this? How do you find current? You might need some clues. Answer, I suppose, is somewhere in the screen. Let's say, you could technically find it as a function of time. We have V as a function of time, right? Before the switch is closed, after the, before the switches, when the switch is open, when the switch is closed. The entire timeline from minus infinity to infinity, roughly we know, right? The voltage. You can technically ask current at any time. Before the switch is closed, current is zero, which is also kind of how we got this voltage to be zero. After the switch closes, how do you find current at any time? Again, let me show you the slide with the answer. Next, to write all this formula, right? Another is to actually appreciate what that formula means, right? Students typically make an exhaustive list of all formulas from a book or a reference. That is not useful if you don't know what the formula is. Asked you a question, I am also trying to get you close to the answer by showing you the answer. It is somewhere in the screen. Where in the screen? You are talking about a capacitor. We'll wait for an answer. Okay, let me ask you a question that I already answered. dV by dt. What is dV by dt? See, notice. So given voltage as a function of time, energy as a function of time. At any time, it's just half CV square. So what is the relation between voltage and current in a capacitor? That is how we started this. ISC dV by dt. If you differentiate the voltage, you get current. And it's things are functions of time here in a capacitor. That's not so in case of a resistor, right? This is what I meant. Yeah, great. ISC dV by dt. This shows that current depends on the change in time. Because the switch is closed, impedance tends to infinity as DC. So DC is steady state. Fair point. Because switch is closed, impedance tends to infinity. But take derivative of differentiate voltage function, you get current function. Notice you are differentiating with respect to time, right? V is a function of time. When you take derivative, you get a function of time, that is current. C is a constant. In fact, let's do that. The discussion doesn't end. I don't tell you that. Brown, green, yellow. Start with this. You can also find the current in the capacitor as a function of time. This happens to be C, D. Take this function, differentiate it with respect to time. Let's do the differentiation, okay? If you differentiate this function, what do you get? You get a C here, this V naught, right? Different derivative of that is 1. Then minus into, there is also minus T by tau. T is what you are differentiating with. So this is 1 by tau into e power minus T by tau. Differentiation derivative of 1 is 1, right? I'm not going to write it down. So this happens to be C V naught, minus into minus is a plus, by tau e power minus T by tau. Tau, tau is RC. So this essentially is, that's kind of, how much space do I have here? Now I have some time. This happens to be V naught by R e power minus T by tau. What it says is that, right? This happens to be V naught. This value is V naught, and that function is Vc of t. You take derivative of this function, you get Ic of t. C of t. Here it is 0. There is actually, I am only taking the part that is at time greater than 0, but still there is a good mathematical way to deal with that. You have Dirac and Heaviside functions, but without complicating too much. The slope is discontinuous here. So there is this function is a slope of this function. This is essentially, find the slope. You get this, right? Because of that, there is a jump, sudden change in the slope. There is this initial value, and then it starts exponentially decay. The time constant of this decay. Here tau is RC. Here also tau is RC. What is the initial value? Initially, the capacitor behaves as if it lets all current. So this initial value, notice this. When t is 0, this is e power minus 0 is 1. So we have V naught by R. Initially, at the initial point, the capacitor actually closes. Eventually, in DC, it opens up. This is exponential decay. This is also, the time constant is tau is RC. So the green function is over here. V naught by R e power minus T by tau. And that is your IC of. So yeah, you can find voltage at any time, energy at any time. You can also find current at any time. It's just a derivative of this function that I have shown here. There isn't any discontinuity of anything like that. It's just like I try to draw it correctly. It's a simple exponential decay. Why do I call that the most important gate topic, right? Because and notice start showing up. And then I think we should stop at 8, but 9 notice your power is integral of E of t. Power is essentially rate of change of energy. So if you integrate energy, you get energy is power is energy per unit time. So given energy, if you integrate it, get power in case you want. And energy is a function of time, energy in the capacitor. If you integrate that let's say 0 to t, you get power. Power is a function. But this is kind of like fairly straightforward, but let's not and just use the definition, but let's not overemphasize that. But in bioinstrumentation, this can get important. But I will finish this with one important thing. The time constants of energy and voltage are not the same. Time constant here is tau. The time constant here is square of this function. That will be 2 tau. You're squaring it, or instead of calling it 2 tau, this is tau by 2. Okay. Let me also make a note of that here. If V voltage across a capacitor as a time constant of tau, then energy of the capacitor as a time constant of V square e power minus 2t by tau. So this has a time constant of tau by 2. So this is actually going faster. It decays or saturates as a square of voltage, right? It actually does faster. This one detail I think we'll revisit in bioinstrumentation, typically in a defibrillator pacemaker circuit. Sometimes if you're doing energy calculations, this gets important. Defibrillator circuit, essentially, typically this is an RC circuit. You're charging a capacitor, discharging it during defibrillation. Pacemaker, again, typically it's a RC circuit. Your load is typically a resistor, and then there is a capacitor that gets charged and discharged. Okay, so if you slightly make some changes here, it becomes a bioinstrumentation application. Whatever the 10 points that we discussed applies to that. They can ask you any of this for a defibrillator or a pacemaker, and there the 10th detail gets important. Okay, and we'll look at it when the bioinstrumentation application, actually, when we discuss that, we look at it. But for now, let me just make a mention. Fine. And all the 10 things that we discussed can also be framed for an inductor. Okay. Let's finish this question. So I said, let's do this question once more. Circuits given below, Vs is 50. Once a circuit is switched to position 2, here, V is, see, for transient problems, this relation is more useful. For any frequency dependent AC circuits, the impedance is important. Okay, so V is L di by dt. Right? Again, if I have to plot things as a function of time, circuit given below reaches a steady state for SPDT switch at position 1. Let's look at the current. Okay, I said at steady state, this thing shorts, right? The time point is over here. So you have position 1, then you make that switch, SPDT switch, goes to position 2, you make that change at time t equal to 0. Okay. So what happens is the steady state current in the inductor. This is, what is the value of this current? So let's draw I L of t. Current in the inductor is a function of time. What is the initial at t equal to 0? What is the current here? Let us test it. So the position 1 steady state, notice this is time is starting from somewhere over here, right? It has kind of reached a steady state. What is the value there? Solve that. And this is position 1. This is shorted. The current is just V by R. The R is 25, V is 2, so I is 2. I happens to be 2. We have to use the same color as this one. I is. At that time, the position switches. What you have here is a circuit without a voltage source, right? That voltage source is removed because the switch moves here. We have essentially a resistor, inductor resistor circuit, LR circuit. Quick way to look at it, whatever energy is there in this, there is some energy in the inductor, it eventually gets dissipated by the resistors. So initially, say this is like for salaried, people, they get monthly salary. Over the course of the month, expenses kind of eat away all the salary, right? this initial energy is this current and this inductor. So there is that can drive current here. That can take care of expenses. Eventually, that gets lost, right? So notice what happens to this current as a function of time. It's a LR circuit. It kind of exponentially decays. L over, how do I say this? This is just L over R circuit. The decay happens at tau is L over R. The initial value happens to be 2 amps. I suppose things are in SI. Yeah, ohm and volt, and all that, they give you amp. Because inductor resist sudden changes in current. So just before, when you are changing the switch here, position 1, just before turning the switch, right? The current couldn't have been very different. That function is exponential saturation towards this. There is a sudden slope change, but it kind of like exponentially from probably from 0, the inductor initially doesn't allow no current, and eventually kind of saturates towards this. How does that happen? Perhaps, this resistance and this resistance are different. So this is position 2 resistance. That would be 50 ohms. Okay. Notice at position 2, you have a 25 and a 25, 25 and a 25, right? Your net R at position 2 happens to be 50 ohms. Okay. And then at position 1, your R1 happens to be just this one resistor, which is 25 ohm. The inductor remains the same. But the point is, these two are happening at different time constants. The time constant here is L over R1. It's actually a different time constant. Technically, given current as a function of time, here you could draw voltage as a function of time. Derivative of this function. Okay. The derivative you could do it. In fact, I could kind of leave that as an exercise. Find derivative of the function. This is fairly easy. You could draw technically VL as a function of time. Okay, you could do that. So V is L di by dt. But what do they ask? Once the circuit is switched in position 2, the energy dissipated in the resistor. All this energy initially, that is the only energy source in position 2, that needs to be dissipated. So what we have here is this. You have a charge. You have a current in this inductor that happens to be I equals 2 amps. That's initial energy in the capacitor that will be eventually dissipated. Okay. So energy, in fact, we should say technically total energy. Energy is presumed energy dissipated in the resistor. Right. At this stage, some of you could wonder, sir, we know current as a function of time, voltage as a function of time. So in the resistor, we know current as a function of time, right? Energy, this is like I square R, power. You integrate that power, you get the total energy dissipated, right? You could technically take that approach, but that is harder. In fact, this is energy. Just made a cardinal sense. Let me correct it. Okay, E by dt is P. Okay. So you get technically what I should have written as the other way. The ninth point, technically, power by definition is energy per unit time. AE by D. So given energy, you can find the power. That is one thing. And given power, I square R, right, in a resistor, you can integrate that. This is a power dissipated in a resistor. You can integrate that and get energy. So they want the energy dissipated in the resistors in this position. Initially at t equal to 0, this is what you have. You could do it by 2 means. You should know both the means. Okay, let me kind of say that. So what is the energy dissipated? This is the question. You can do that with 2 methods. It's also contrast method 1. This is hard method. Technically, I is a function of time. This is an exponentially decaying function. I inductor as a function of time. Right? In the circuit, this also happens to be I resistor as a function of time. Right? Power in the resistor, power dissipated power in the resistor as a function of time. It's just resistance there are two resistance, let's say equivalent resistance into I square R of t, I square R. So in fact, notice if this is decaying with a time constant of L by R2 e power minus t by tau 2, right? This power will be square of that. Tau power will be tau current, right? Tau current. They do have very different time constants. Voltage and current have the same time constant, that is tau. But power will have a different time constant. Because of the square, this will be 2. So you technically know power as a function of time. And these are simple functions. Okay, this is essentially notice I naught, the initial current, into minus t by tau 2. Okay, and this technically becomes R equivalent I naught square e power minus 2t by tau. Tau 2 is because at position 2 we have a different time constant, right? And then this 2 because we are squaring the current. So this essentially is power as a function of time. You know, power, you can find energy in the dissipated energy, total dissipated energy, right? Total energy dissipated in a resistor equals, you can integrate this power functions from 0 to total energy. You have to integrate from 0 to infinity. The area under that exponential curve. This happens to be a curve like this. The total, at any instant, the power as a function of time. If you integrate all of that, this total area, power in the resistor as a function of time, you can get the total energy dissipated. This is method 1. This is hard. What is this? Power as a function of time, and then finding the area under. There is also an easy method that we discussed, end of class yesterday. So these are extraneous. Let me erase them. The total energy dissipated in the resistor was initial energy stored in the inductor. Initial energy happens to be half Li square. You know the initial current. So can we quickly do how much is this? I think you gave an answer yesterday. This is I is to inductance is 0.1, 0.2 joules, right? 0.2. How can we write this? What is this? What is the principle we are applying here? When I say this, the total energy dissipated in the resistor, what is the principle we are applying? This energy equals that energy. I gave a lunchbox analogy, right? Lunchtime, you open the lunchbox. Okay, you and your friends complete that lunchbox. The total amount of food that you and your friends ate is the initial amount of food in the lunchbox. You took some time to eat it. Eventually, the lunchbox got empty, but the initial food in that lunchbox quantity is what everyone eventually ate. Right? For a lunchbox, it's mass conservation. What is this? Not a hard thing. So I am going to wait until we have an answer. Yeah, this principle of energy conservation. Energy conservation. And this method, of course, is homework. You can do this because I did this capacitors. Here, can you do that kind of energy conservation? There is this energy input. One of your friends is continuously buying candies from a nearby store during lunchtime, right? This is this DC source. So when you have that source, you have to account for that. You have to deal with it differently, right? Even if the switch is closed or not, the source is always active. The energy supply is there. You have to deal with that scenario differently. But here, this is a lunchbox scenario. You can, no additional terms. Kind of energy conservation still holds there, but kind of it's much simpler in this scenario. Okay, in position 2, it's much simpler. Great. So the answer is 0.2 joules. Yeah, I already did this. Now we have to move on to AC circuits. So mnemonic L equals lunchbox scenario. So fine. I mean, this probably now this inductor capacitor. See, the reason to actually pull that lunchbox into the picture is to actually give you a mnemonic, but they are asking you for total energy dissipated and all that. Lunchbox can certainly serve as an anchor or a mnemonic. Also, from a perspective of a lunchbox, it's actually fairly straightforward, which is why, more relatable and, we could associate with that better. Yeah, if it helps you remember this energy conservation and how, it's actually complicated. This is a exponential decay, square of that exponential decay, integration of the square of the exponential decay, right? It takes a lot of time to actually do method 1. Well, if you do this lunchbox thing, yeah, fairly good. You get the answer in one line. If it helps you, helps as a mnemonic, that's very good. So I have to conclude here. What you really need to know are two things. Having said all this, I'm still sir, too much things. This condensed version is condense the condensed version, right? Genuine concern will also address transient circuit, transient RCMR. Okay, you have a resistor. I have V is IR. This is not transient. This is not this, and then P I square capacitor. All you need to know, as far as this transient is concerned, all you need to know is IC dV by dt, and then energy is half CV squared. Perhaps one more thing that I would add, tau is C. You may have to do a R equivalent or a C equivalent. Now, multiple capacitors, you can do a equivalent capacitor. Multiple resistance, you can do a Thevenin resistance or equivalent, typically equivalent resistance. For an inductor, we have D is L di by dt, J is L I square. Okay, this is a function of time. Not function of time. This is a function of time. Okay, this is a function of time. This energy. This is a function of time. Energy. This is a function of time. So we have voltage as L dVt. Energy is half Li square. This is a function of time. 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 And here you have tau is over R. So multiple inductors, multiple resistors, two equivalent here. So rest of it, in all of the rest of the things are all essentially consequences of this. Notice, in fact, that is what I wrote down. Then one step down the line, Laplace transform, Fourier transform, do this, and all that. This equations means no sudden change. Then eventually at DC, this thing opens, this thing shorts, and all that. It's all consequences, right? So this is all we need to know. Now let's move on to this circuits. Okay. Notice the typical concepts here. What typically happens, switch opens, close. The switch open, closing. It becomes is an resistor circuit. This you know how to handle. Energy conservation, know how to handle. Now the transient response, things are functions of time, graph, equation, any particular value. Now what we have to do was impedance and impedance. Okay. We have to do impedance and impedance. That is what is left. And we'll finish that. Right. Let me just change this file. And this is, we are 1 hour down the line, 2 hours down the line. I have many PYQs. So again, if you know impedance, we can technically do this very fast. But if I have to explain complex numbers and all that, this is going to take time. There is one bit that I want to discuss. There is something called a phasor representation. Okay. So notice here what you had RC and LR circuits. Typically you have a switch, and I said this becomes a resistor, right? You typically have a switch, and there is a steady state that you are displayed. That is one thing we saw. And then time constant tau is RC, or you have tau is L over R. That is something. Then we have the energy conservation. All these three things from a C circuit. We have seen this from a DC circuit perspective. Okay. Now, what you should recognize as, see, when we made this transition, this is familiar ground, familiar, easy, home turf, right? Yeah, you can use many other words. So perhaps it might have been a hard problem, moderate problem, but the moment it's a resistor circuit, it's very familiar and easy. You should acknowledge us in case of AC circuits. We have RC or L or circuit. You know what this reduces to? This again reduces back to a resistor circuit. There is something in this arrow that makes it a resistor circuit. Does anyone know what that arrow is? And the point being, that simple change, you are into familiar, easy, home turf area. You are into your own, playground, your backyard. You know how to play there. One word fills this arrow. Consider that as a plan. 1 year takes you from a RC LRC or a LR circuit. In fact, I would go C circuit, LR circuit, CLRC or RLC circuit. Even second order RLC circuit becomes a resistor circuit. One word. And what I mean here is whatever most of the things that you could do in a resistor circuit, voltage division, current division, KVL, KCL, right? Bridge balance, bridge imbalance, finite bridge, infinite bridge. Most of the things that you discussed in a resistor circuit can be done. And this conversion, as you can put one letter there. You don't even need one word. Can someone guess what that word is? That one letter is Z. If you look at the impedance of any of these elements, you can treat it as a resistor. Whatever calculation you did with a resistor, you could do that calculation with an impedance. Only difference being impedance is a complex number. You have to do complex algebra, not normal algebra that you did with a resistor. There is an imaginary part and then there is a real part. There is a magnitude and then there is a phase. So the magic word is impedance. So let me start with the condensed version of that. Okay. You have a resistor, you have a capacitor, inductor will go. You have an inductor. What you need to know here is V is IR. You need to know here is V, complex numbers, I'm going to write it this way, I times C. What is C? V is this complex number. Notice, essentially, again, if I have to be slightly, notice, V is IZ. V, now this is a function of frequency. Frequency of the AC source matters. Frequency of this source matters. This impedance, again, is a function of frequency. The Z happens to be, what is this? The impedance of the capacitor? Ratio of voltage to current, 1 by J omega. Okay. Now, you can start filling up this side. Voltage is I times C. This is of omega A. This is of omega. This is of omega. This. And then you have Z of omega equals J omega. Yeah. What is this J? J is square root of minus 1. Of course, this is a function of omega. The point is, whatever, most of the things you could do here, V is IR, you can actually do here. What all the basic resistor questions that we did, concepts that we did, are applicable here. But now our task is to understand a couple of things. First, let's stick to this. Let's make sure we get the units correct, okay? SI units. As far as you stick to SI, you don't have to worry about any of that. You have voltage, current, energy, power, right? And then you have capacitance. Then you have omega. This goes by the name angular frequency. Angular frequency. Then you have frequency. Then you have a time, okay. Time. Then you have time period. You have T, C, R. Yeah, this is a time, I suppose. You don't have to write that. Perhaps you need to know time constant. Tau, okay. Tau, or in fact, tau, T is there. This is time constant. This is time period. This, of course, is resistance. This is inductance, self-inductance. There is a mutual inductance. How two solenoids interact, that's a mutual inductance. This is self-inductance. There is no mutual capacitance, at least in the linearized version, so we have a capacitance. These are the variables. Then we have the SI units, right? We have SI units. H, volt, amp. What is the energy units for energy and power? SI units for energy and power. We have joule. We have watt. How is volt, amp, and joule related? Simple. Use, this is VI, right? You can use it. This is essentially volt, amp. Okay. Energy is essentially is volt, just voltage into current. Energy is, notice, power is rate of change of energy, dE by dt, energy per unit time. So essentially, you could also write this as joule per second. So there you got watt, volt, amp, and then joule second all connected, right? Volt amp is 1 joule per second. That is 1 watt. Let's finish the easy ones, okay? Time period, seconds. Resistances, you have this symbol O, right? And then L is 3. This is farad. Hey, what is this farad and all that? How does it relate to one of the things? You can use a known relation. Energy is half CV square. You kind of know how that is farad, how things are related. Tau is RC. Notice, right? You know many things, right? So, tau is RC says, notice, this corresponds to ohm farad. Ohm farad is essentially time. How do I get that? This also corresponds to Henry by tau is RC and tau is L over R. Okay. So these are SI. As far as you stick to them, you are going to get one of the other units. If there is any prescript, that is, if there is a micro or milli, that just gets transferred. Okay. There is a millivolt, do some calculation, you end up with a milliwatt. But volt gets to a watt. So from SI, you move on to another SI. What is left as this frequency? Time period is also thus. What is left as omega, F, and T. The units for omega is radians second. Yeah, this is, let's say this is radians per second. Okay. Frequency happens to be number of oscillations per second. Essentially, this is hertz. 1 hertz by definition is per second. You could say number of oscillations per second, or you could say number of revolutions, number of beats per second. We have seen many examples of this, right? Number of revolutions per second. 1 by j omega c, it's an impedance at the end of the day. You're getting a ohm resistor like term. So where is this? It's not 1 by RC, right? 1 by j omega has radians per second. Capacitance is, question is 1 by j omega c. Does it correspond to 1 by second? No. Like 1 by RC, then it's 1 by second, but no. And in fact, see, I already told you, if you know complex number, if you know this impedance, is essentially any circuit is a resistance circuit, you can solve all of the gate questions. But another huge real trouble here is with the units. Okay, and units, they typically set a trap. No, 1 by j omega c is not 1 over second. Okay, this is incorrect. 1 by RC will be, 1 over second. RC is second, right? I put that here. Notice, this is essentially RC. This is L over R. That corresponds to actually second. Okay, this won't be 1 over. You get a clear answer? This essentially has units of ohm resistor. Here, notice, things are oscillating as a, when you're looking at things as a function of time, they're oscillating. What is the time period here? Fairly easy. This is time period. So let's kind of highlight that part. What I have here is one oscillation. One oscillation, essentially one revolution, that is essentially 2 pi. Okay. This is one full circle. You get back where you started. So this corresponds to 2 pi radians. One full circle. One oscillation is one full circle. That's all I say. One full. Omega says how many radians per second. You have speed as distance by time, right? You have omega is essentially speed. The distance it travels is pi radians. Okay, one revolution, 2 pi radians in a time period. This is the relationship between omega and t. I just used distance by time. Nothing more there. Perhaps I can emphasize that. All I'm using is, notice, speed equals distance by time. Angular frequency or angular speed. Okay, you could call this or speed. Okay. Omega, the distance it travels is one revolution, that is 2 pi. One complete circle. The distance it travels, 2 pi, one full rotation, that is 360 degrees or 2 pi radians. How long does it take to do that? One time. This is one important relation. This is one relation. 1 over t is related to one of the other variables here. Can someone spot it? 1 over t, this time period, actually related to, if length of one heartbeat is just how many heartbeats per second, there is, it goes by a number. So can someone spot that? 1 over t is related to one of the variables here in the stream, just that list, forget energy power, you have omega, you have tau, T, even forget resistance. Definition 1/T is frequency. Great. This is again by definition. There is a definition of frequency, number of oscillations per second. And if you use that, you could also write this as 2 pi. That's a somewhat of an important relation there. I kind of omega by 2 pi is 1 by T. That is correct. That is essentially frequency, right? Omega is 2 pi f. Yeah, great. All of you are giving the correct. Okay. And because, okay, general, someone asked, right? Hey, does 1 by j omega c, does it have units of 1 by, second? No, I said no. But I'll add something here. So time constant is RC. This is L over R. I always say, they are asking you for a frequency. You don't know which frequency. There are 3 frequencies. Okay. There are 3 magic. They are asking for some frequency. Last 15 minutes of the exam. Instead of randomly guessing a numerical answer type version, you can actually do some calculation and may enter a more sensible answer. Or if they are asking you for frequency. Okay. And I'm going to refer to that as magic frequency. For an RC circuit, that magic, they are asking you for some frequency, lower corner, upper corner, bandwidth. What is the frequency at which, some frequency. Okay. I don't have time to solve the problem, or I don't know how to solve the problem. In that worst case scenario, let me be very clear. Okay. This is worst case scenario. Last 15 minutes, I don't know how to solve, but I want to give a sensible answer. Worst case guesstimate. Okay. For an RC circuit, that frequency, F, for an RC circuit happens to be 1 by 2 pi C. 1 by 2 pi RC. Let's see if someone can complete this. For a L over R circuit, that is LR circuit. Can someone say what? L over, I like to call it L over R, but you can, LR circuit. What is this magic frequencies? Can someone guess from what you have seen so far? That is, they have given you a circuit, AC circuit, the inductor and resistance. They are asking you for a frequency. A typical best guess is this, magic guess. That often gets you the right answer. And you can kind of stare at this equation and tell me what this should be. This is in hertz. This will be in hertz. Let me write it down. 1 by 2 pi L over R. If we have to isolate the time constants there, actually the time constants are there. L over R and O. So 1 by 10. Okay. This happens to 1 by 2 pi tau. This happens to be 1 by 2 pi tau. There is a relation between parameters in the transient circuit and parameters in the DC circuit and AC circuit. This, the transient circuit is a time constant. In the AC circuit, it's going to be the frequencies. Okay. But here you could actually, so this suggests, in fact, Janil asked a question, right? Notice. Omega will be 1 by 2 pi F is omega. That happens to be 1 by RC. Omega again is 1 by, right? Notice 2 pi F happens to be 1 by RC. 2 pi F is omega, so that's what I'm making. F 1 by RC. That tells you omega is 1 by tau. That is, if there is a relation between time, given time constant, you know the angular frequency. And angular frequency is different from frequency. One has units of radians per second, another has units of hertz. This is a very, very, very typical trap. Let me complete notice. Angular frequency is radians per second. This is hertz. This is the biggest, most common trap in the GATE exam. They give you a frequency based on the units. You have to decide whether they are referring to angular frequency and frequency. Right? Even if you are trying to calculate something like time period, notice. Given frequency in hertz, time period calculation is 1 by that. Given frequency in radians per second, time period calculation is 2 pi by omega. You can easily enter an incorrect answer. So be careful about it. And I just now showed that there is also a relation between that omega and tau. Okay. And okay, this trap here has to do with the units. Okay. Omega happens to be 1 by tau. I just, if you know tau, you can calculate the angular frequency of a circuit, RC circuit, LR circuit. And there is a final magic frequency. This is for a RLC circuit. Does anyone know what this magic frequency is at least? RLC circuit, they are asking you for a frequency. You don't have time. What is your best guess? I'll show you, examples from this is all formula units and all that, right? Quickly start showing you examples. Get examples. 1 by 2 pi. Can someone complete this? Complete third magic frequency. This is for a second order circuit. See, it is for a second order circuit. They are asking you for a frequency. That is, you are looking at a circuit with a resistor, capacitor, and an inductor. All three are there. They are suddenly asking you for what frequency. Worst case scenario, my guess is case scenario. But we'll also start looking at some best case scenarios. Okay, the time delay between peaks of the voltage signal V1 of t to cos 6t. Technically, this is conventionally this notation is used, but there is a problem here. I'll tell you what the problem is. But there are many problems with this particular gate question. One is the answer key is incorrect answer key. Official answer. They make a lot of mistakes actually. Okay. I thought they were trying to set a trap. No, they have made a mistake. I'll show you what that mistake is. One, and this is notation. This is actually poor notation. This is in degrees. Typically, this is in radians. One part is in radians, one part is in degree. You are adding them. You need this is in radians typically. This is in notice degrees. So you are adding the two. It's conventionally used. Understanding is that here the phases I am representing by degrees. It essentially by 60 degrees I can convert that to radians, right? If I am plotting a function, I am doing the conversion and do this addition. Okay. There is some, this is typically inconsistent notation, but we'll have to live with it. Consistent notation. Okay, unfortunately, this is convention. Inconsistent conventional notation. Top of this, they set a trap, and here they fell it. They fell into their own trap. So inconsistent conventional notation. So there are many things stopping you from getting a marks in this part of circuits question. Okay, one of them being units. But my suggestion is, as far as you stick to SI, you are doing good. Understand what basic omega is, basic Fs, basic time period is. You can derive all of this. You don't have to memorize them. Okay, all I did is just do speed, distance by time, and one definition, that is 1 by TSF, right? You can pretty much get all of that. So trust in SI unit to deal with, know what the SI units are, hold on to them. Okay, that will help you deal with the SI unit problem. 10 minutes, you don't know, they're asking you for some frequency, you don't know what that frequency is. The best case is this. Best case, worst case, best guess. You don't know the answer, but you want to guess. You want to guess, sensibly guess. That is the worst case, best guess scenario. The three numbers that I have given you. Any frequency they are asking. Based on the circuit, plug in one of these three numbers. Sorry. That is the suggestion. Okay. Now I'm going to answer this question. Time delay between 2 cos 60 plus 60 degrees and minus 360. You can answer this in two ways by knowing some convention. But, for now, I am going to actually plot these functions to make sure you see what is what and all that. Okay. I'm going to plot and answer these questions. Can someone type these two things in the chat window so that I have access to that? 2 cos 60 plus 60 degree. Can someone type that? Can someone else type minus 3 sin 60? We'll find the time delay by plotting, and then we'll come back here and see what the answer is. And while that happens, can someone also hey, pi is approximately 3.14. How much is this? How much is this? How much is this? How much is this? 300 pi by 360. Can we get all those numbers also? Okay, thanks. So one curve is minus 3 sin 60. Someone else just type in this 2 cos 60 plus 60 degree, because I'm going to get out of this file. I still want access to those details. And can we also have these numbers? Type in 300 pi by 360 equals this. 10 pi by 360 equals this. 50 pi by 360 equals this. 200 pi by 360 equals this. Okay, thanks. So 2 cos 60 plus 60 degree. Now, most of you are picking 300 pi by 360. Some of you just go down the line because, redundant work. Just fill in these 4 numbers so that we can verify what we're saying. And at this stage, so this is in radians. Supposed to be whatever you put inside that box should supposed to be in radians. So notice you can read the omega to be 6 radians per second. So when you multiply that time, you get this number is radians. This number is degree. Let's also calculate that. I'll put 60 degrees happens to be how many radians? That calculation I can do. 60 divided by 360 into 2 pi. I suppose this is 1.046 radians. Can someone also type this? Okay, 60 degrees. This. Let me at least write down all the numbers, type that. 60 equals degrees equals 1.046 radians. 300 into 3.14 divided by 360 happens to be 2.616. Okay. And they're supposed to be in seconds. Okay. So this is in seconds. 10 into 3.14 divided by 360 is 0.8, 0.872, approximately 0.87. Okay. Then we have 50 into 3.14 divided by 360. This is 0.436. Then you have 200 into 3.14 divided by 360. That is 1.744 seconds. Okay, some of you are answering answer D, answer K, but this is incorrect. This is the correct answer. I can also tell you that right answer. Again, verify that. Professors are also humans, right? I think gate committee is also humans. Perhaps there is a committee, they could have avoided it, but does happen. But the real problem is, they don't acknowledge or accept that they have made a mistake. Okay, even in objective scenarios like this, they accept to, they stick with their mistakes. I don't know where that is, how scientific or how rational that is. Hey, I have typed in. Can someone just type this? 60 degrees is 1.046. This is this, because I'm going to shift this, right? I need this reference. 300 pi by 360 equals this. Can someone just have that in the chat? None of you want to do that? Okay, thanks. 60 degrees is that. Oh, Kirtana kind of typed all of it. Thank you. So I think she saved all of our types. Okay, so let me just open a browser. Okay, let's plot and see. Hey, technically we can answer that question in 30 seconds. But notice the committee has made a mistake. Right? You can get the correct answer in 30 seconds using some simple convention. But given that the committee has made a mistake, okay, this is like often not understood correctly. The numbers and terms here are not often understood correctly, which is why at least if you are seeing some number in the question, what is that number, right? I want you to make better sense out of it. And most of the place where the students really gain or lose marks is subtle differences between what is angular frequency, time period, and all. That's where most of the marks is lost. Conceptually, things are not hard. They don't test you very hard conceptual things. If you know impedance, you are good. Okay. For that reason, I'm going to spend time while discussing PYQs. I'm going to spend time plotting all this. Let's go to keep. Okay. Great. Let's see this. Cos x. Cos x is this. Compared to this, how should cos 6x behave? Frequency smaller, that is more oscillations or lesser oscillations? Simple question. 6 is this. What will cos 6x more oscillations? 6 more oscillations per second. This is 1 radians per second. This is 6 radians per second. The blue curve oscillates 6 times more compared to this. Let's see what count that. Where here is one full wave. How many oscillations are there? 1, 2, 3, 4, 5. If you're kind of careful, I think you'll get 4, 5, 6 complete oscillations. Okay. Yeah, if you're careful, you get 6 complete oscillations. And to make things easy, let's also make this step size in terms of pi. The cos curve, if you look at it, in 2 pi seconds, this axis in seconds. Whatever you're putting in is second. 1 second. Make it actually more convenient. Let's make it t. Let me do t. Let's make it cos of an angle. Let's make sure we agree with the units of X, okay, because many of the differences we are going to read it from here. This is fine. Yeah, is there a way for me to add text? X axis is in time. What we are looking at is a function that oscillates as a function of time. If you look at cos x, when time equals 2 pi, okay, it finishes one full cycle. That is, the time period is 2 pi for cos x. One full cycle from 1 to 1, the amount of time it takes, the time period for repetition is 2 pi seconds. You can calculate it. So in 2 pi, essentially 2 into 3.14, it will be 6.28 seconds, okay? This time period is. If you were to look at cos 6x, 6 is in radians per second, x is in second. So both of them multiplying each other, you get, now the input here is of course, it's an angle that goes into cos. It oscillates 6 times faster. If you look at from 0 to 2 pi, where there was one full wave, the red wave, there is one full wave. Now we have till here 1, 2, 3, 4, 5, 6. 6 full waves. So the frequency of this is one red curve is 1 oscillation per second. Frequency of this is 6 oscillation per second. Or the oscillation, this oscillates 6 times more. Okay. Time period of the red curve is 2 pi. Time period of the blue curve, can we quickly tell that? It's 2 pi by 6. That is essentially pi by 3. Agree? It is 6 times, oscillates 6 times faster. So the length of one full wave is 2 pi by 6. That is pi by 3. We also let me write down all of this. Yeah. Cos x time period is pi seconds. Cos 6x time period is 2 pi by 6. It's 6 times faster. This is pi by 3. Cos 6x is 6 times faster compared to cos x. It's relatively 6 times faster. 6 times faster. Let me ask one more question and then I'll move. Okay. Frequency of cos x is dash hertz. Can someone just complete the dash so that we can move on to the way to save this? Time period I put, can you just calculate frequency? That is, 2 pi is essentially approximately 6.8 seconds. Can someone calculate the frequency of cos x? Time period, frequency, right? Fairly simple. Why is there a value like rate? Janil says 0.159. That's what I also had. This is 0.15. 0.1. That's great. So most of you, 0.159, 0.15, 0.16, fairly good. Most of you can see that, right? So you understand this. Right now, notice. You understand this angular frequency of cos 6x is 6 rad per second. So when your x is time, you put in there, you get a radian, you get a degree, and then function with this. For simple calculations, time period, frequency, angular frequency calculations, I suppose you all could do. And at this stage, I have shown you all the relations, right? I'm going to presume you can move back and forth from one to the other. Great. Let me turn off this red curve. Let's get to this blue curve. 4 oscillations per second, right? It's oscillating faster. Frequency is higher. That we can fairly see. This is oscillating for where it's doing 1 oscillation. This is doing 6 oscillations at the place of 1 oscillation. Let's look at that. Okay. So question here, if we put add a phase. In fact, let's kind of compare this. 6x plus a. Let's also kind of, at the stage zoom in. Let's see what that phase is doing. Compared to the blue curve, let's, initially set the phase at 0. Phase is also in radians. So you're adding radians and radians, right? When you say cos 6x plus a is a, phase a is in radians. Okay. So when you add a phase, when there is no phase, both the curve lie on top of each other. When the phase is positive, how should this blue curve move? If A is positive, should it move to the left or right? In fact, let's see that, okay? Phase is positive. This curve is moving to the left. It's appearing faster compared to the blue curve. At t equal to 0, the blue curve has a peak. Green curve has a peak slightly before that. It has a head start. This number is positive, it has a head start. This curve is moving to the left. If it is negative, it is slowed down. It is moving to the right. But when the phase is, one complete frequency, it's a complete circle, you are going to get back at this. After some time, say minus 6.3, we made that calculation, right? 6.28. After one time period, phase corresponding to 2 pi, right? Or like one complete, phase difference is 2 pi, it's a full circle. Cos theta plus 360. You got back where you started. Notice minus 6.3, right, is 2 pi. One complete delay is one complete oscillation. So phase is moving it left and right, and how it moves, this negative and positive phase that we have seen. Right. Now, the two curves in the question, we have cos 60 plus 60. So at this stage, notice, changing the amplitude is not going to change the phase. I can change the amplitude, but the relation between the phase difference between time delay between the two curves remains the same. So I'm not going to bother about the amplitudes given in the question. Okay, I'm only going to consider this. But if there is a sign change, I'll have to account for that. Okay. So one of the curves given in the question is cos 2 cos 60 cos versus 6x plus 60. 6x. And I suppose 60, we calculated that to be 1.06. Okay. And the amplitude doesn't matter. For that reason, I am taking off that 2. The sign will not. Again, things are cluttered. Let's turn this off. Let's turn this off. This is one of the curves given in the question. 2 times that, I'm not going to follow. Other curve is sine 6. Yes. Notice sine 6x and minus, the sign really matters. That is minus sine 6x out of phase by 180 degrees. Okay, they are out of phase. This is essentially this is 6x, so they are out of phase by 180 by 6. That is pi by 6. Okay, so this curve is given. This curve is given. The sign matters. The amplitude doesn't matter, but the sign matters. So I have the curve with this sign. So these are the red curve and the green curve are given in the question. Do you all agree? So what is the time difference between the two curves? There itself, the peaks are here. We can see, the positive peaks are at the top, the negative peaks are at the bottom. Let's say they are referring to positive peaks. The question is the time delay between the green and red peak. There is a different time delay between the red and green peak. This is different. This is different. Is there anything in the question that says minimum time delay, maximum time delay, any of that? No. But let's find the time delay between these two. What this x is 0.872, okay, minus this, how much is it? Pi by 4. Can someone differentiate these two and tell me? The time where this peak reaches is 0.8728. The time where this reaches the peak is pi by 4. Can you calculate the delay? 0.87. This is pi by 4. Amplitude is 1. Peak happens. If you just multiply it, okay, the peak, this axis will remain the same. If it just, any of you like questioning that, I can also show that quickly. Can you find the difference between 0.8728 and pi by 4? This reaches a peak at this time, this reaches a peak at pi by 4. What is the difference between them? Any of you are wondering, sir, what is given is 2 cos, right? Just to show that if the peaks happen at the same location, I'm going to go thus 6 plus 1.046. Okay, just to show that the peaks are at the same location. The amplitude doesn't matter. Peak is occurring at 0.87. The peak 1, okay, 0.87. Okay. This peak 2 is occurring at 0.87. The peak location doesn't change. Okay. 0.87 roughly, that's where the peaks are happening. So, did anyone calculate the difference? Again, let me leave the number. The peak here happens at 0.872. This peak here happens at 0, pi by 4. A difference between the delta t here. Why is there a confusion, or why is there a surprising amount of delay? Show you, sir, in a GATE exam, how do you plot Desmos and all that? How do you find the peak? Some of you are wondering about that. Hold on to that. I will show you how to find this in a GATE exam. But here, is there anything wrong with the connection? Extremely good. No issue. But is the question not clear for any reason? Find the time delay between the two peaks. I'm showing you where the first peak is happening, where the second peak is happening. What is the time delay between them? How long? Oh, what is the time difference between the two peaks? Internet is on. Numbers not visible. Is that the case here? I don't know. In fact, I'm surprised. One number is pi by 4. Other number is actually slightly above pi by 4. Pi is at 3.14. 0.8728 is like slightly above pi by 4. In fact, if you're wondering, pi by 4 happens to be 3.14 divided by 4 happens to be 0.785. I'm asking the difference between 0.785 and 0.872864. Okay, roughly 0.09, 0.08. We made some calculations earlier. Do you see which of the options this actually corresponds to? Thanks actually Ayush for, generally responding after a long time. Which of the numbers in the question it actually matches to? 10 pi by 360, right? It's there in the chat. 10 pi by 360 happens to be 0.08. They said is a correct answer and I just showed you by plotting things. And here itself, I pointed out one issue, that is time delay between peaks. There are actually two different time delays. Between this, there is a small time delay, then there is a large time delay. And if you consider positive and negative peaks, there is a time delay between this red peak and green peak. In between and all that, there are other time delays, right? If the question is ambiguous. But okay, let's give some credit to them. They are referring to the positive peaks. Answer is 0.087. That happens to be 10 pi by 360. What they have given, I'll also show that. What I have plotted here is cos 6x plus 1.046 and sin 3x. This is sin 6x, the blue curve. Okay, notice sin 6x and minus 6x, the peaks are happening at very different, positive peaks are happening at very different locations. Okay, so this is a very different curve. I take sin 6x, but if you scale it, the peak remains at the same location. Okay, if you multiply by 3, it remains at the same location. This is cos 6x. Now let's look at the difference between the peaks. Now again, there are two differences. There is this large difference, then there is a small difference. Let's actually find the small difference. We highlight the two numbers. The first peak is happening at 1.037. Okay, that is 5 pi by 12, I suppose. The second, okay, roughly, approximately this. Okay. Okay. I got the exact number. Yeah, this is the 0.87 we initially had it. This peak. Oh, I got 1.037. The 5 pi by 12. Yeah, these are two numbers. What is the difference? Time difference between these two? 5 pi by 12. You can convert that. Find the seconds. This second, what is the difference to that? And in fact, check which of the options. Many of you made that calculation, so I'm going to, let's finish it in 30 seconds or something. This is 0.4355436. That is option C. That is the official answer. They are not asking for the time delay between cos 6x and sin 6x. They are asking for a time delay between cos 6x and minus sin 6x. That happens to be this. Notice if I scale it, okay, this location is not going to change. 0.786 is not going to change if I multiply it by 3. Some of you have said there is that 3 factor of 3, where is it going? Because where the peak happens, that doesn't change. Right? Notice if I multiply by 3, that peak happens at the same point. 0.78, right? We have seen this. Pi by 4. Okay, the peak location doesn't change by multiplying by scaling by a positive number. But if you change the sign, the peak location changes. This is still at pi by 4. Okay. But the reason to spend so much time is not really to say, hey, there is a gate mistake. One is the correct answer is different. And I wanted to show that point number 1. But the real thing is, most of the marks are lost or gained in the simple things that I mentioned. Difference between angular frequency and frequency, time period. Simple calculations is where most of the marks is lost. Do you see, can you make all this simple calculations right now? That is my only question. And if you have any question with the time difference that I showed, raise it, okay? I'll also go back and show how to do that in a gate exam. 30 seconds without Desmos, how to do that, I'll show you. In 30 second, 1 minute calculation you can do. But this requires some prior knowledge. Let me also share this graph so that we have a copy of that. Someone put this in the WhatsApp group so that I can later make use of it. So the correct answer is B. Answer K is this. That happens to be actually, technically, and I am presuming this is positive peaks, min delay between positive peaks, because there is also another solution there, min delay between positive peaks. The question should have been clear, it is not. And their answer essentially is min delay between positive peaks of cos 60 plus 60 degree, and it's not minus, it's plus 3 sine 60. Okay, they have made two simple mistakes. Question is not clear, answer is incorrect, but the real blunder is they didn't accept any challenges. Okay? Not fair. I hope someone challenge. I asked students to challenge it. Perhaps no one challenged, so they didn't really make a blunder, but it's a mistake. Okay, how would you do this in the GATE exam? Add your playlist. It is publicly available. I gave it to you a few weeks back, asking you to watch this one playlist. It's extremely useful, both for impedance, phasor thinking. There is something called phasor, where you don't really worry about what this frequency is. Okay, that is all these oscillations and all that you're not bothered. All these oscillations you start looking at in a circle. Okay, this is things are going round and round in a circle, and your phases are different locations in the circle. Then you have also draw the circle slightly smaller. The cos corresponds to x-axis of the circle. Okay, this is your 2. This corresponds to cos axis. Theta is a circle, right? Goes on and on oscillating. So this corresponds to cos axis. Okay, the angles are measured positively this way in the circle. Theta, positive theta is thus convention. Note as, so this is cos theta. Where is sin theta here? Cos theta minus 90. If we take cos theta minus 90, happens to be sin theta. That is, if you backtrack from cos, you end up with sin. This happens to be sin theta. Sin theta is at this point in the circle. Cos theta is in that point in the circle. This is known as a phasor representation. Phasor. So now what is given as 2 cos 60 plus 60 degree. Let's plot that one. Okay. This is, so what I have here is cos theta. This arrow corresponds to 2 cos 60 plus 60 degree. So this angle is 60 degree. And someone tell me, where is this arrow? Minus 3 sine 60. Forget even, the 3. Where is minus sine 60? 6 really is immaterial. Okay? In a phasor representation, let's say the 6 is immaterial. Can someone tell me where that? So minus sine is at 180 degree phase difference from sine, right? Great. Okay. I mean, negative x-axis, actually, Madhurima, we're very, very close. That is opposite of sine theta. I suppose you wanted to say x-axis, cos theta has taken it. Negative y-axis, sin theta has taken it. Notice this. I think you're correct. Yeah, you meant to say that. Actually, it's the y-axis. Negative y-axis, sin theta took it, right? We already saw this. Notice in the notation, you can easily write down trigonometric relations. Hey, sin theta, you add 90, you get cos theta, right? All of those reactions you can easily get. Yeah. I kind of got what you are saying. So this is where minus sine 60, the time delay between them. So the yellow is rotating, oscillating the circle. The rose is oscillating the circle. Okay, the delay between them is, this is the time delay, time taken for yellow to traverse. This is the time taken for yellow to traverse. This is the delay. Required time delay, okay, is time taken. Traverse or move, traverse. What is the angle? 30 degrees. Traverse 30 degrees. How much time it has? Notice. 60 degrees corresponds to t. This says time taken for, so to traverse 360 degrees, it takes one time period. To traverse 30 degrees, it's a fraction of one time period. What fraction? Just someone plug in the time period here and tell me which of the options it is. So given omega is 6 radians per second, okay, we're getting omega is 6 radians per second. What is the time period? And you can just plug that over there and tell me the final answer. So this implies your time period is, you all said this formula, right? And this is how much? Pi by 6. And just plug that in over there. So that corresponds to a fraction of the time period, that is 30 by 360. and the time period happens to be 2 pi by 6. So which of the 4 options? If you plug in t as 2 pi by 6, what do you get? If you want me to simplify this English, make it more clear, 360 degrees take t, 60 degrees take t seconds, therefore 30 degrees take the fraction of, small part, take fraction of t, that fraction is 360. Just plug in t, you should get one of those 4 options. Yeah, 30 by 60 is 0.83. You had to calculate it, but okay, let me also complete that step. Therefore, 30 degrees take 30, this fraction of t, that is 30 by 360 into 2 pi by 6. That is 3 into 2, 6 cancel, you have 10 pi by 360. And that happens to be 10 into 3.14 divided by 360. This is approximately 0.087 we saw in that decimal speed. The answer key is this. That is actually referring to this. Answer key is referring to this time delay. That is not. And when I discuss solutions for this, I kind of say, I'm not sure they are referring to positive and positive peaks, negative peaks. And I thought they were trying to be smart and set a trap and all that. No, they have made a mistake. Hey, are you getting B? Any of you? Sir, what is this? Cos theta is here, sin theta is here. Then plot, it's just the time taken to traverse the circle. Required time delay is time taken to traverse. You have doubts on what this convention is, Phasor convention, that you have to, some prior knowledge you have to do. I try to introduce it, x-axis is cos theta, negative y-axis is sin theta. See, you get the trigonometric relations. Time delays correspond to calculating this, time taken to traverse all these angles. It's hard to be more concise and also more correct. Most of them are fairly straightforward. All you have to do is stick to SI units. You are good. Yeah, because sine and minus sine have 180 degree phase difference. Sine is negative y-axis, minus sine is positive y. Good question. Convention is x-axis is, let me also explicitly write that. Phasor convention. What color do we use? Blue is not used. Phasor convention. Your cos theta is x-axis. Your sin theta, this is minus y. Sir, why minus y-axis in the convention? Because that's when we can get correct trigonometric identities. Point number 1. Notice cos, that is cos theta minus 90 is sin theta. It's not cos theta plus 90. Plus 90 is not sin theta. Plus 90 will be minus sin theta. Okay. This convention will get you correct trigonometric relations. And there is, of course, one more thing in the convention. And you have clockwise theta is positive. That is the convention, Phasor convention. So in this convention, minus sin theta is on the y-axis. Fair question. Okay. Now, how much time? 4:12, right? I have. Go till 4:30. I have stick to conventions. Okay. Know what the standard units are. Many of these details doesn't matter. You should be able to calculate omega f tau t. Understand the difference between omega and f. One is in radians per second, another one is hertz. Understand the difference. How to calculate going one from the other. I showed you what these numbers are. We did some calculation just now, right? Omega is 6 radians per second. What is the time period? 2 pi by 6. Right? Did that. Omega is 2 pi by 6. T is 2 pi by omega. What is that? Essentially, it's speed is distance by time relation. So you can calculate one given the other. In fact, you can also calculate time constant, right? You can do all this. I showed an example, and then so if you stick to SI, you are also good with all this, right? Ohm, Henry, Farad. You don't have to worry about units. That is one thing that I tried to tell you. So stick to SI. That or just be aware of what omega f tau t is, and then typically traps are set there. There is the Phasor convention. Let's summarize that. We should technically warm down. I kind of know the discussion was kind of like intense, right? One question, I also had some digressions on magic frequency and all that. One question, but it's a problematic question, and all the things that you need to know are there. So discussion was intense. We are supposed to warm down, but let me see if we can hit a home run soon after we warm down. Okay, so stick to SI units. Point number 1. You are good. All confusions with the this ohm, Farad, Henry, Joule, watt, all of that. You should be safe from all of those. step to yes. But if there is a milli or a micro, keep that milli or a micro in the calculation. Unit should be, the set should be easily traversable. Omega f t easily traversable. That is given one of this, you should find the rest of that should be easily traversable. One you should find the others. That is another thing that we learned is there is a phasor convention. They had this digression magic frequency. Magic frequency is the worst case scenario, best guess solution to this min-max problem, right? They get exam. So magic frequency. The point of all that is impedance. I didn't get time to explain this, but I mentioned impedance is resistance for AC circuits. So whatever you treat it as a resistance circuit, whatever you could do with impedance. If you know complex algebra, impedance is resistance for AC circuits. This is what you kind of need to know for first order, second order, any frequency dependent analysis. What I have mentioned here, if you know that, you're good. What I spent time on is I tabulated all the SI units. We made what is this omega I of t tau. We are able to do that. On that, I did this. So tomorrow I'll try to find examples from the tomorrow next class. Impedance is the resistance of AC circuit. In fact, if you know that, you can answer most of the other gate questions. And then magic frequency, let's see if there is a need for a worst case guess. If we need to guess, but typically we can answer. Okay, that will do. But let's look at these questions. Okay, this is I think there is an ambiguous question. There is a mistake in the question. I'm not going to solve that. I'll give you some pointers. So from the frequency response side, what we really need is there is resonance power factor and all that. But notice that's not complicated. I'll just tell you what is what. Perhaps the solutions are already available, right? You could come prepared before the next class, but notice circuit shown below. It's observed that the amplitude of voltage across a resistor is same as the amplitude of the voltage source. So voltage across, amplitude here is essentially the amplitude here. Okay. In simple English, the impedances of that happens when impedances of these two cancel each other. 1 by j omega c happens to be j omega L. When that happens, this amplitude voltage will be this amplitude voltage for this circuit. You can easily find it. Notice on 1 by j omega c equals j omega L will tell you actually omega square is 1 by square root of LC. You got the magic frequency. Even if you did not know anything, if you a LCR circuit, magic frequency is 1 by 2 pi square root of LC, you can get that answer correct. This is frequency in frequency in hertz. Question is asking you frequency in radians per second. Okay, so that will be 1 by square root of LC. If you get that, you could answer this question. I told you the two answers. What the question, the condition stated in the question means the impedances are the same. You could answer. Fine. First case scenario, what can I guess? Magic frequency, guess the magic frequency, you can get the correct answer. Okay, let's look at this question. Let's put it in. For the circuit given below, choose an angular frequency omega naught at which the voltage across the capacitor has maximum amplitude. There is a resistor, there is a capacitor and all that. What do you know? You know voltage division. You know impedance of a capacitor. Apply voltage division. Answer is 2 lines down the line. It's 2 steps down the line. 2 steps away from it. It's just question and voltage division. Let me traverse further. A series RLC circuit, 220 volt, 50 hertz supply for a fixed value of R. Inductor is varied to maximum current. This value is this. Corresponding potential drop across a capacitor is. Inductor is varied to deliver maximum current. The maximum current happens when the resistance is the least. The impedances of capacitance and inductance cancel each other. When will that happen? The magic frequency. Omega square is 1 by square root of LC. You have one piece of information. And then to find that omega, you have another capacitance or that, you have another piece of information. Capacitor is, potential drop across a capacitor is this. If you use the impedance, you can do this. So it's a combination of magic frequency and voltage division using impedance. Let's go here. Series RLC circuit consumes power. Value of L is changed such that circuit consumes same power but operates with a lagging power factor. So here you need to know what is power factor, but at the end of the day, there is a simple sign change in impedance. Plus 10J is becoming minus 10J. So the difference is 20. That is what they are stating here. Initially, it is some XJ. it becoming minus xj. What is the difference? 2xj. Okay, it boils down to the simple impedance calculation. So the power factor and all that, that is what it boils down to. You can answer this question. And notice power factor is a favorite topic of that. We'll have to deal with it on its own. Again, there is a kilovolt amp and AC supply. It's a lagging power factor, right? This is some theory. There is a 5-10 minute video that I have put up and that explains this concept of power factor. If you watch that, that suffices to answer this. Okay, and that brings us to some miscellaneous questions, some BJT MOSFET approximations or models. We have dependent current source. The current here is 100 IB is this, right? The KVL, KCL, you should actually solve this. There are some miscellaneous questions. So by now we are actually done with circuits. We'll come back, we'll spend one more class and we'll finish this. Okay. So most of the questions in electrical circuits you can answer with this. Impedance is resistance for AC circuits. Stick to SI units. You don't have to, there is no headache of units. You should be able to convert a given F, find omega, given omega, find T, given tau, find omega. Make that simple calculations. And typically traps are set in the units of that. Omega is in radians per second, other one is hertz. Phasor convention that I explained today. This is all the convention. Cos theta is x-axis, sin theta is minus y-axis. Why? All trigonometric relations holds good. You can calculate the time taken to traverse given angles. That is the Phasor convention. And then magic frequency, worst case, best case scenario. RC circuit this, LR circuit this, RLC circuit this. I already showed you an example. Notice what they are using for is 1 by square root of LC. Okay. Perhaps we all need a break. So let's take that break. It would really help if you watch the impedance playlist, biomedical signal processing or biomedical filters playlist. Short videos. It would really help if you come prepared. It will also help if you watch that 5-10 minute video on power factor. I also put up that. So if you come prepared, we can just, there is no more theory here, okay? Whatever I wanted to tell you, we couldn't solve a lot of problems, but whatever I wanted to tell you, I told you. The theory is here, okay? We'll quickly solve all the gate examples and we'll wind up with circuits, okay? So 2 actionable items, ball is in your code, 2 actionable items, short playlist given a couple of weeks back, 1 video, 5-10 minute video. Then we are finished with circuits. Okay. Beyond this, we are already getting 80% of circuits questions. So beyond that, doesn't really make sense. Okay. So this is a good place to stop, and we'll finish the circuits next class.